Okay, cool. So today I'm going to talk about equity in resident crowdsourcing, measuring underreporting without the use of ground truth data. So this is joint work with my advisor, Nikhil, at Cornell Tech. In modern cities, what we call resident crowdsourcing systems are heavily relied upon to learn about on-the-ground problems in real time. This includes the 311 systems in North American cities, which is effectively a number you could call to report problems such as potholes, bed bugs, power lines, and in our application, trees. As an example, the New York City's 311 system received 2.7 million requests in a year alone. So to help us understand what is going on, I'm going to show you what happens, so the pipeline of events after a tree falls in the city. So after a tree falls, a good neighbor comes by and thinks, okay, this is a problem, I'm going to report it to 311. And this accounts for roughly 70 to 100,000 reports per year to the New York City Parks Department. About 65% of all those reports gets inspected, and about half of those inspections lead to a work order in the end. In this work, we're focusing on the first part of this pipeline. That is, we want to understand the reporting behavior of residents. More specifically, our goal is to measure underreporting. So what we define as underreporting is the phenomenon that after an incident happened, different people reported at different rates. Now, there are different interpretations of this word rates. What we're mostly concerned here is the speed that people report these incidents. The importance of measuring this is that we have a pipeline of events, and reporting is a very important link in this pipeline. So if there are inefficiencies and inequities in this link, then it affects the end-to-end efficiency and equity. Why is it hard to measure? Well, to put it very simply, it is very hard to distinguish the case between fewer incidents and lower reporting rate if we only looked at the observed unique incidents. So let's take this toy example. Suppose we have 10 broken trees and half of them gets reported, versus we have 5 broken trees and all of them get reported. Then from the perspective of the Parks Department, these will look exactly the same. This problem is brought upon by the fact that we have no ground truth data about the incidents. This is because, well, for New York City, we have 700,000 street trees, and it's simply infeasible for the Parks Department to inspect them all in real time. Hence, we say if a tree falls in the city and no one reports it, then the city doesn't know about it. So for this work, our contributions are twofold. First, we propose a very general method to measure underreporting without the use of ground truth data on incidents. And the second is that we apply it to New York City Parks dataset, and we uncover some very interesting results. Okay, without further ado, let me introduce you to the data generating model for the resident reports. So a couple of preliminaries. We use theta to decode the incident type, which includes geography and incident characteristics. So we say that an incident of type theta occurs according to some hidden process. So we're not imposing any further assumptions about this process that incident occurred, because this is the whole point. We have no ground truth. After this incident happened, we assume that people report this incident according to a Poisson process with rate lambda theta. Now, this could potentially be non-homogeneous, but for the purpose of tractable estimation, we're using the homogeneous case in our paper. This incident, after it's reported, might be inspected by the Parks Department, and it eventually dies at some unknown time, which might mean it's fixed by the agency or it's just washed away. So at this point, I want to make 2 comments about this Poisson assumption. So this is generally true for public incidents, so for power lines and street trees, whereas people report it independently and people make duplicate reports. This is generally not true for private incidents, such as bed bugs, which is kind of a limitation of this. The second comment is that with a homogeneous Poisson process, the significance of the rate is that it implies the delay between the incident happening and the first report came in, which the significance will come about later. And with this model, our research question is very straightforward. So how does this reporting rate lambda theta depend on the type of the incident theta? Well, this research question has been brought out previously. And previous methods can generally be characterized into two categories. So some of them are quite naive, which just compare the number of observed unique incidents for each type theta. And recall that this suffers from the exact problem that we talked about. The other type recognizes this problem, and they construct proxies for the hidden incident generating process, and then compare a function of the incident generating process and the observed unique incidents across all types theta. So the problem with this type of methods is that the accuracy highly depends on the quality of this proxy. And without ground truth data about the incidents, it's hard to calibrate those proxies. So to overcome the problems faced, we have mainly two insights. The first insight originates from the missing species problem literature, which states that duplicative reports about the same incident tell us the reporting rate. So in the ideal world, if we want to use the duplicate reports, we want to know about when the incident occurred and when it died. Had we known these two, it's just problem solved. It's a standard Poisson rate estimation problem, very easy. But the problem is we do not observe these two times. So this prompts us to the second insight, which is how do we construct an appropriate observation interval such that we can do such estimation. Our task has two criteria. The first is that we want this interval to be such that the reporting process looks like a Poisson process with exactly the rate lambda theta. The second criterion is that we want both A and B, so the start and the end of this interval, to be observable so that we can work with it in our estimation. So this theorem establishes sufficient and necessary conditions for the first criterion to be met. We first need the interval to be contained within the birth and death. And second, we need both the start and end of this interval to be stopping times. Let me briefly explain to you how things could go wrong if these two are broken. So let us say we select A to be the time of the first report. So A satisfies both these two criteria. But for the first condition, let us say B is sometime after the incident has died. So obviously, the Poisson rate estimator will be biased downwards. To break the second condition, let us say that B is the time of the last report, making it not a stopping time. Then the Poisson rate estimator will be biased upwards, because we are systematically excluding time in which we know the incident is still alive, but no reports came in. So to find an interval that satisfies the second criterion here is purely a design choice. In our implementation, we chose A to be time of the first report, so satisfying both these two conditions, and it gives us the maximum amount of knowledge about each incident. For B, we use this rather complicated specification, which is a minimum between the inspection time and a number of days after this start of the interval. So the claim that the inspection time is a stopping time is justified by the fact that the scheduling of this inspection is determined largely by outside factors, mainly the availability of the inspectors. And we use this truncation to mitigate anomalies in the data, mainly overdue inspections. So in our implementation, we actually chose T to be 100 days. And after some robustness check, we find this to be a nice compromise. OK, so let me briefly summarize our empirical methods. For each incident I of type theta that we observe, we will construct this interval as we've just described. And we will count the number of reports inside this open interval. So in the example above, we're only counting the second report. Then the number of reports will be distributed exactly as a Poisson random variable. so we can apply some Poisson rate estimation. Then to answer this research question of how this rate depends on the type theta, what we implemented in the end was actually a variant of Bayesian Poisson regression to tackle the problem of high dimensionality in the type theta, because theta it encodes geography, and we're actually using census tracts. So there are thousands of them in New York City alone. We assumed a very generic dependence on theta for lambda theta. And there are two variations that we had to make. So we observe a very small percentage of duplicate reports, which prompted us to use a zero-inflated Poisson model. And also, since we're using geographical variables, the coefficients for the dummy variables for neighboring geographic regions, they might have some correlation structure within them. This prompted us to use some form of autoregressive priors on those coefficients. Okay. Here is a brief introduction of the data that we used. We basically used public data that's augmented with internal data on those inspections. They account for 115,000 inspected service requests made to the Parks Department over a 3-year period, and of them, 16,000 were duplicate reports. So the graph on the left shows the constructed observation interval, so you can observe the truncation at 100 days. And the graph on the right depicts the number of duplicate reports that we observe in the data. So most of the incidents actually only get one report. So there are 0 duplicate reports. The choice of covariates that we included in theta mainly include 3 types. So the first are the location, which are the census tracts in New York City. The other type would be the incident characteristics, and these are both reported by the residents and by the inspector. Okay, so here comes some of the main results. Along the efficiency line, we actually see some good stories. So here we have the coefficients for 3 of the reported incident categories. What we see here is the general trend that more urgent incidents get reported more frequently. So for example, on average, hazard events, which as the name suggests are more hazardous, they get roughly 4.22 times higher reporting rate than removed tree incidents, which are less hazardous. However, along the equity lines, we are observing some very, bad news. So so we plotted all the coefficients for the census tracts of New York City on the map of New York City. The way to interpret this plot is that the darker the color means that the lower the reporting rate in that neighborhood. So for those of you that are familiar with the geography of New York City, you might notice that Staten Island and Manhattan, so those two historically very well-off neighborhoods, generally have higher reporting rates. Since there is a lot of socioeconomic clusterings in New York City, this might intuitively suggest that there are disparities along the socioeconomic lines. And we do substantiate that claim in our full version of the paper. So as we mentioned before, that the reporting rates imply the reporting delays. This is very substantial in practice as we contextualize them here. So among different types of incidents in different neighborhoods, there is a substantial gap between this reporting delay. For example, in Manhattan, a hazard event might be reported just 2 days after it incurred. But in Queens, some other types of incident might take more than half a year to get reported. This is important for at least 2 things. The first is the management of downstream operations, in which we can balance and counter for this imbalance of reporting delay. The other thing is it might be very important for the allocation of 311 publicity efforts, because 311 system is fundamentally a system for residents to call for allocation of public goods. And a more balanced and more equitable use of 3-on-1 system is very desirable for city governance. Okay, so just some quick conclusions. So this work, we work towards understanding underreporting in resident crowdsourcing systems. We propose a general method to measure underreporting without ground truth data about incidents. And there are mainly two insights. So the first is the use of duplicate reports, which helps us disentangle incident occurrence and the reporting behavior. The second is the identification of observational intervals, which allows for a Poisson estimation. We believe this is widely applicable to settings where the above two are possible. So maybe software bugs reporting is also fall into this category. We also do an application to the New York City Parks Department data, and we uncovered a lot of spatial and socioeconomic disparities. And this likely serves as a very first step to understand and optimize the end-to-end efficiency and equity of 3-on-1 systems. Okay, so I'm gonna put the link to the full version of the paper here, and I'm happy to take questions.
So we have time for questions.
Do you have any estimates of the truthfulness of reports in different geographies? So you reported on the rate of reporting, how quickly things are reported. Do you get any estimates about how likely it is that there's a false alarm?
Yes, that's a very good question. So we actually have a parallel work to this that when a report comes in, we will estimate the probability that this report is actually truthful and that the risk reporting contained in that report is actually truthful. So it's kind of tangential to this work, but that's a very good problem, and we're working on it.
Do you have any sense of whether your identification is coming from the Poisson assumption, or whether it's like do you have any result on non-parametric identification?
I don't actually have a very good estimate for that. So yeah, so with Poisson estimates, the good thing is that we have a large number of off-the-shelf Poisson rate estimation techniques that we could use and to identify the dependence of the rate on those types. With non-parametric methods, as far as I'm concerned, I'm not aware of that many methods. So, but that could be a very good direction in the future.